Okay guys, give a look here. 2019 question 1. So it starts off there with describe metal fatigue and hardness. So describe. So fatigue is failure. No, fatigue sounds like, a runner being exhausted after maybe running miles of repeated pounding steps. So failure due to repeated loads or cycles. Okay, so it's kind of like a runner's, their legs are gone, after millions of repeat loads on the calves and the hamstrings and all that. So it's the same thing for a metal, you could say, e.g. in car suspensions. Okay, after, maybe hundreds, thousands or millions of shock loads. The shocks, the shock absorbers need replacing. But it could be, or in hinges, or in maybe hammer drill chucks. Okay, where you've constant pounding, hammering cycles. So fatigue is basically repeated loads, millions of them. So that's fatigue. The next one there is metal hardness. Now hardness is the ability to withstand wear or abrasion. So basically, if you think about it in terms of metals, it's like how easy is it to foil it? And the easiest example to picture there is cast iron, like the voice. Not that you should ever put a foil up to it, but if you were foiling a cast iron, it would be very difficult to foil it. So a cast iron is very hard to cut or foil or work or remove metal compared to, I'll say, mild steel or copper or aluminium. Now the only thing I will say there is that even though something is very hard, it mightn't be tough. Okay, but hardness is often linked with brittleness. Okay, so cast iron is quite brittle. Now that was A. Now A part 2 there is describe with the Edwards diagram a test for hardness. Okay, so I'm going to just draw, because this specifically said that they wanted a diagram, so I'm going to just draw a little bench machine here, something like this. We'll just put a platform . Okay, just a platform there like that, and we're gonna have, or here's our machine. Here's our platform. Up above here, we're gonna put a spindle and an indenter. Okay, now the test I'm gonna say that this is, it could be, I'm gonna say this is the Vickers pyramid test. But it could easily be the Brinell ball or the Brinell cone or the Rockwell ball and corner. Like there's other tests, but they're all the same principle. Okay, so the Vickers pyramid test. Okay, and if I zoom in on this here now, here is our metal. Here is just a point of our indenter, and so there's our metal. Okay, so a hardened indenter shaped like a 136-degree pyramid is pressed into the surface of the metal. Okay, so this is, if I was to use some colors again here, I'll just go with blue. This is our indenter, and here's our test piece. And this is the zoom in on it then. So here's our indenter point here. And because that's the point of it, it's an upside down pyramid, that's going to push in there with force, okay? So that kind of a ram comes down there with force and drives the pyramid down into it. And what that's going to do there then, so hardened indenter pressed into the surface of the metal, the hardness is calculated by the diagonal of the indent. Now I'm going to use a diagram for that as well. So if you were looking down on top of that piece there, so there's your metal piece, that's going to leave you the print of an upside down pyramid. So it's going to be like this. This is looking down from above here now. And it is the diagonal of that. So I'll just take a line out from here and a line out from there. And I'm going to call that D there. That's our distance. Okay, and the softer the metal, the deeper the indent. Okay, so the softer the metal, the deeper the indent, and the bigger the distance. Okay, so on the, obviously if it's a hard metal, it's the opposite then. A hard metal, and you could easily say that there, that a hard metal would give you a small indent, and that's good. Okay, so a hard metal gives a small indent. Okay, so that's loads on that. The second part here then, we have our, so the results were got from a tensile test. So that's in the form of a stress strain, and there's two of them, but the stress goes up to 425 and the strain goes up to 8. So 425. So I'm just going, if I went like 50, 100, 50, 200, 50, 300, 400, 450. Okay, so if that was 0, 100, 2. And then the strain goes up to 8. So I want to spread this out here as best I can. So I could do it in 8, and I don't want to go 16 because I'm after coming in so far. So I'm going to go in 15s for 1, 2, 3, 4. So 1. So that should cover so I'm going to just put a few light lines up here. Okay, now I'm reading off the table, just put that there. So I'm reading off this table right here. So obviously you're going to need to be looking at that to do it. So, okay, so metal A. So metal A has at 0.5, okay. So these are my stresses. And down here is the strain. So stress is force over cross-sectional area, and strain is extension over original length. So sometimes that question can be given with force and extension, but so it's not always stress strain. So I'm just going to get halfways on this here, because our first measurement was a 0.5. Okay, so metal A, I'm going to do metal A first. There's 4 points for that. So we've got 125, which is our first one. Then we've got for a strain of 1, it's 260. Then for a strain of 1.5, it's 400. Which is here. And a strain of 2 is 425, which is there. So if there's an elastic region, and there usually is, the first couple of points here will be a straight line, and then it curves off. So that there is metal A. Almost definitely a cast iron, because it was very, very strong, a long elastic region, and then it just snapped. Now, metal B then, so at 0.5 it's 30. And at 1 it's 60, so that's 50. So 1.5 is 87. Okay, so 50, halfway would be 87, would be around here. At 2 it's 110. At 3 is 135. At 4 it was 150. At 6 it was 162. And at 8 it was 140. So I'm just checking to see, was there a straight line elastic region here? There was. But then after that, so this is metal B. So that stretch to load didn't take massive force on it. So I would say it's probably something like copper, aluminium, something like that. So we were asked there, this is part B, we were asked to draw that graph and describe with the aid of a diagram the type of fracture that will occur when A breaks and the one that will occur when B breaks. Okay, well that's actually easy enough, because metal A was very strong and brittle. Okay, it's because there was little, that's elastic, and then once it starts bending it's plastic. There was little plastic, I'll call it deformation. So that's going to give you, this will give a brittle fracture. Now, brittle fracture, I could sketch it up here, I suppose, that when our dumbbell shaped test piece breaks, and just make sure that's on camera, there it is. So when that breaks, it's going to be there's our test piece broken, and if you could zoom into the front view of that, it'll be pretty much flat across. So I'll just put a tiny bit of colour on that so that people know what I'm talking about here. So that would be a brittle fracture. Now metal B is going to be different. So metal B, when it breaks, is going to give you what's called, okay, it doesn't really make a difference that I've drawn over the thing there. So metal B is going to give you a ductile fracture called a cup and cone. So I'm going to there's our broken test piece, but if you could get in and look at that from the front, it's going to give you, that's our cone, and we're going to just go the opposite here at the other side. This is our cup. So you just want to be able to sketch that. So this is our cup, and this is our cone. Sorry, I have them the other way around now. God. This is our cup, and that's our cone up here, and that's a cup and cone. And so this will give a brittle fracture, and metal B gives a cup and cone ductile fracture. Okay, so it's really like a picture is worth 1,000 words there. Like if you can sketch those there, and that clearly shows that you understand it. One example of a metal that's consistent with them. So as I said, metal A could be cast iron, and metal B could be copper or aluminium. Alright, now on to C then. Okay, so C, there are non-destructive tests in the design and maintenance of a wide range of components. So one application for each of the following methods. So a use basically for visual inspection would be large cracks on the surface. So large cracks on the surface of, let's say, an object, e.g. plane wings, are meant to be visually inspected. Okay, so you'll see a large crack there. Now the dye penetrant would be small cracks on the surface, not visible to the naked eye. Okay, so the dye penetrant, did they ask to explain it? They didn't. One application for each of the following. So we don't have to really talk about it, but the dye penetrant, where you pour out your dye and wipe it all off, and then you put it under a UV light, and that. Now it said outline, so that will do for outline. And the next one there then is the magnetic particle test. Now the magnetic particle test would be, because it's magnetic, it would be cracks or surface defects on magnetic metals. Okay, so yeah, cracks or surface bars on, so it has to be on metals that are, you know, magnetic. And the last one there then was the eddy current test. Okay, so the eddy current test would be suitable for defects near the surface. And near the surface. So often they're on stuff like non-ferrous, like aluminium, or copper, stuff like that. Okay, so the next thing there is to describe with the aid of a diagram then a suitable radiography in DT. Okay, so basically if you see radiography, that's part 2 there. You're talking an X-ray test, so you would have up here is going to be our emitter, and we're going to just put a metal object down here. Doesn't really matter what it is. Let's just draw something like this. And down below here, we're going to put our X-ray film. Okay, so basically what happens there, I'll try using a color here, is here's our X-rays penetrating the metal, going down onto our X-ray film here. And what I'm gonna just, a nice way of doing this now is if I put in a defect here. Okay, so let's say there's an air pocket inside and that. There's our metal. So that's an internal air pocket there, a defect. So that's going to show up down here. I'll just line it up a little bit. And that's going to show up on our on our X-ray. So the defect, we'll just try and explain that there now. The internal void slash flaw shows up in the X-ray. And that's our X-ray now more realistically now would be all another way of showing this up would be maybe you could connect this back if you wanted to and just sketch this as a monitor or a display, and you could have something like I'm not sure what's the best way to show that up there now, something like a black patch showing up here on our part, something like that would do. So you could say that's your monitor. So you know, that or like this, but just have some way of showing X-rays penetrating a piece of metal and, you know, some kind of a film or a monitor to display it. So that would be more than adequate. That would be good. So yeah, best of luck with that, people.